In the last tutorial, we started with slope stability using slide, and we talk about the limit equilibrium analysis, and we had an introduction about how to start to model this using slide. Today, we are going to use a different software called GeoStudio, and this software can analyze the slope with two different ways, either using a strength reduction method and either using a slope limit equilibrium. We talk in details about both in the geotechnical engineering course. So now we are going to talk about how we can implement this using GeoStudio. So I will start with the same model we created for slide, and this is the model. As we can see that this member was 40 meters and this is 20 meters and 15, and the slope was 2 horizontal to 1 vertical. So we will go now to GeoStudio, and if you looked at the window of the GeoStudio, you will find that there are different modules for the analysis: slope W, sweep W, sigma W, quick W, and temp W, and others. We will talk about some of them later, but today we will just start with slope W. If you started with slope W, who will give you this window of defining the analysis. So I will define the analysis as slope W. So here you can choose the analysis using either limit equilibrium analysis or sigma W analysis, which use the strength reduction method. We will start with limit equilibrium analysis. In the limit equilibrium analysis, there are different ways to analyze your model between Bryce or Spencer or other, or Bishop or Spencer. So I will choose Bishop as we did before. So I will start like this, and I will start like this, and here this is, we can create it Bishop, and we can delete this one because this is comes from the same one. So we will just we will not consider any bore water pressure now. So I will say now close, and this is the window of the GeoStudio. Let's look more closely about the window. Here we can draw many things. We can draw different stuff here in the window. If you want to, here there are file, there are view, there are define and draw. And in draw you can draw region and point and load and other. You can here sketch something to facilitate your analysis. So if we went to axis here, and I can change the units into metrics, so we have to change the units. So if I went to units here, I will choose the length to be with meter, and temperature would be Celsius, and the mass to be with kilograms, and force to be in kilonewton, and energy to be in kilojoule. So I will say close. Now I will go back here to sketch axis, and now we can see that all the dimension has moved to be in meter. So I will choose the x-axis to be 45 meters, minimum, sorry, to be 0, and the maximum to be 45 meters, and for y to be 0 and the maximum to be 25 meters, and I will say close. So this will be my axis now. So this is my area of work. So here you can do the different stuff. If we went back here to here to my AutoCAD, I can move this to 0 and 0, and I will create DXF So I will go to here to show menu bar. And I will go here to select everything, and I will go to edit, and I will select from edit copy with base point. So I'm choosing this is to be my base point, and I will go here to make it Control V. Last time in GeoStudio in slide we can import as we will see in further videos, but here we will just in GeoStudio we will see how can we start with import. So this is my model here, and I will save it as DXF. Here, and I will close it, and I will go back here to GeoStudio and file, import region, and I will go to get this from desktop, and he didn't get anything. Why? Because if we went back here and we opened our DXF, we have to go here and say joint, and we select this one and close, and I say save as DXF, save, yes, and close. I will go back here and I say file, import region from layer 0, and I say okay, and here is my problem. This could be because of the dimensions here. In meter it's not the same in AutoCAD, and because if we went to unit here, we can see that our dimensions here in inches, so we have to change it to meter, and we say okay. So if we start to measure now, and we say save, so it will be hard to draw from AutoCAD because I started there in inch. So I will just start drawing here, and it's totally fine. So I will just check the units here, view, units, and meter. And I will go here to grids, and X will be 1. And now I can draw easily. I can just come here and I start to sketch lines, or I can draw region. So from here you can go up 15, and you can come here until it's 25. Like you can see the coordinate here, and you can go up here until it's 15, 20, and then here, then here, then here. So you already draw your region, or you can insert this from here. So we already draw our region, as we can see here. Now, after we draw our region, we can split it if we want from here to here. And now we go to material, and we can define material. We can add first material, and we can call it sand. And there we will choose more column, and unit weight was 19, cohesion was 0, and phi was 32. And we say will be like 1, and we say add. For the other material, it will be more column, and it will be clay, and phi will be 0, cohesion will be 10, and unit weight will be 15.5. And we will say close. So here for sand, we will define all the domain to be sand, as we can see here, and as we can see here, this is the limitation of the failure. You can adjust the limitation from here if you want. And then here we go to draw, and we can come here to define project properties, as we can see, and we define geometry properties, and it's in 2D dimension, and this is really important. And since we started wrong, we should have started in feet, so the thickness would be 1 meter. Close. And we go here to region. We already draw our region. We have 2 regions here. And material, we already defined our material. And we'll talk about this later. Probabilistic and reinforcement function. Hydraulic, we will talk about this one later. Slip surface, you can define your slip surface. So you can define it from range here, as we can see, it's from as we can see from left to right, so we are correct. And for the slip surface option, the entry and the exit, and this is the number of critical slip surface. We went the just one critical slip surface, and we can add grid here, or we can just keep it entry and exit, and he will check it by default, or we can define it in our way. So if we let it to define it by our way, as we can see here we will start to draw our slip surface grid. And we will define it. X increment will be 1, Y will be 1. Oh, number of increments, so we will say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll say 20 by 20. So this is my grid now, and we can make it 40 by 40. So here the software is more complicated than the other one because this is more sophisticated, but we will check the results now. You can draw slip surface radius, and he will check in this area. Now we can go here and we can start to save our model, and he's running now, and we will check the factor of safety. So as we can see here, the factor of safety 1.5959. Let's go back here to this, and we will start to remember what was the factor of safety. I will say delete, and the material will be sand. And don't forget that we didn't add a load here, so I will just go now here and I will remove this load. So I will go to loading and I will delete the load, and I will just run the analysis and I will see the results. And the factor of safety here, oh, we didn't we're still adding here a seismic load. We'll make it 0, and we just need to check the material strength, and here was 22, and I will run it again, 32, sorry. So this is 1.525. So this is for the first one, and we can see this is a critical failure surface. Here 1.559, so 1.525, and this is for Bishop simplified, and this is for Bishop as well. So we can see that we obtained, even the shape of the grids here is the same, and this is the critical failure surface. If we went here, we can find, we can look here, and I can tell him uh, show me the low slip factor and show me invalid everything, and auto select the critical, and this is the range, and you can view your results as you want. You can show contours here, all the contours here, and you can show map. You can change these colors if you want. You can show legend here. As we can see, this is the legend. You can draw graphs, and you can draw many things here. Draw contours, so this is for the contours. So let's go back here to the definition, and we will change this analysis. And instead of we define it, we're gonna make it automatically, and we're gonna say close, and we will start to run. Now we can solve and we can check. So this is for the left side. So for the left side, this is the point from 0 to 15, and this is from, oh yeah, sorry, from 0 20, and this is until 40. And we can run. So if we did it like entry, like we had to show everything, so the factor of safety here become 2.8, because now we define this is the factor safety because he chose it randomly. So let's go back here and we will define another failure surface. And we will run it again. And we find that from data entry it's 2.8. So we will stick back again here to the data entry, back to grid, and we say close, and we run our analysis one last time, and we show all the results now, and we see this is our critical failure surface. So now if we added, go back here and we start to add, define, and we can start surcharge load. We can start to add one. We have to enter them manually. So for X it will be 25 from 0, Y 20 to 20, and Y will be X will be 15. It will be 10. So this is the length of the line. We're gonna make it 13, 15, 14.99. So yes, he doesn't want to interfere with this line. So I will say close, and I will run my analysis. Now as we can see, this is the value. We'll go back here, define seismic load, we can hit 0.2, and we say okay, and we run the model. So we can see it decreased to 1.0. So we go back again here to definition, define surcharge load, and instead we make it 10. Close, run. Last time we added it 0, so the value was the same. Now this is the value 10.00. I will go back here to draw to definition. So in the definition here again, I will go here to define surcharge load. As we can see, I will make it 100 and it will be normal, close, run. And this is the critical surface as we saw before. Here, comparing to here, this one. I will go back here to the definition. I will go here to define and I will go here to seismic. I will make it 0. I will say OK. I run last time. So this is the value. Definition, define. You change the load as you want. And this is the surcharge load. Here we bring it back to vertical. So I will stop the video at this point with Sloop W from GeoStudio, and in the next video we'll talk about how to model this using strength reduction method in Sloop W. See you next lecture and thank you.